So what we're going to talk about now is how to design a Memoizer, and you'll see how this gets used. And we'll talk about how to use the Java ConcurrentHashMap class to design our Memoizer. In a nutshell, a Memoizer is used to cache the results of function calls and return these cached results for whatever input you give. So if you have input, you compute the results, you cache it, and then if the same input comes again, you just look it up in the cache. So memoization is an algorithmic technique used to optimize programs by storing or memoizing the results, so you don't have to recompute them, but you just look them up. And here's basically how this works. If you have expensive function calls, something that takes a long time to compute a result, then what you do is you check to see whether or not the result is already in the cache, and if it is not, then you perform this long-running function to do the processing, and then you store the results of that long-running function in a cache, which is implemented as a hash map, and then you return the value that was computed. So those are the steps. If you look up the same result again and it's already been cached, then you just return that result. So it makes things a lot faster because on the subsequent lookups, you resolve it immediately and you don't have to wait for it to be recomputed. So it's there to speed things up by effectively caching the results, which is what a cache does. Okay, so what we're going to do is we're going to define something called a Memoizer, which is a class that will cache the values associated with keys. So as you're going to see here, we're going to have this method that we're going to use to do this caching. And this implementation is a variant of something in the Java Concurrency and Practice book by Brian Getz and colleagues. The funny thing is that one of the first printings of the book, whoever the proofreader was, didn't know what memoization was. So they changed it to memorization. So they called it a Memoizer, which was pretty funny. I think they may have fixed that in later printings of the book. So what happens here, if you already have a value for a key in the map, you just return that value rather than reapplying a function. And you can use this thing anywhere a function is expected. A function is a functional interface defined in Java 8 where you can apply some computation to a parameter and get a result back. And as we'll see here, you can do things like have a prime checking Memoizer, where you're going to, given a value, you'll go and look up in the map, see if you've already computed whether that value is prime or not. If not, you will run a function to compute whether it's prime or not, store the result, and then return it. And the subsequent time you come along, it'll just return the result if you look up something that's already been computed before. And what's cool about this is you can either make it a Memoizer or you could just give the function directly. So you can decide whether to make the optimization, and it's completely transparent to the code. So this code here is going to look the same irrespective of whether we have a Memoizer in place or not, which is cool. And we'll look at that next time. Internally, we use a concurrent hash map to minimize synchronization overhead. A concurrent hash map is a really cool Java concurrent collection that maps keys to values using very clever synchronization techniques to minimize locking for both reading and writing in the hash map. And we'll talk more about that mechanism later. There's other mechanisms in Java that are synchronized collections. They only have a single lock, whereas a concurrent hash map has multiple locks. So it's way, way, way more scalable and way more efficient. The apply method in our Memoizer, which we get because we implement the functional interface, uses the compute if absent method on the concurrent hash map. And that will only run a function if we don't already have a value associated with the key. And basically, here's how this works. This is what's sometimes called atomic check then act. You can read more about check then act semantics here. And what it does is it'll go ahead and look up in the map. If it finds a value, it returns it. Otherwise, it calls this mapping function, which computes the value, stores it in the map, and then returns the value. Here's sort of the equivalent way of doing things if you didn't have this cool feature. This is not atomic, but imagine there was a lock wrapped around it to make it atomic. So it basically kind of effectively looks up in the map, see if there's a value. If there's not a value, we apply the function, If the result comes back non-null, we put the value in the map under the key. So that's sort of the semantics of what compute if absent does, but it does it much more efficiently and much more cleverly than that. What's also cool about this is the way it works under the hood, and we'll look at this in more detail later when we talk about future tasks. If multiple threads simultaneously call compute if absent for the same key, because they're all looking up to see if the same value is prime, only one computation is done. The implementation is super clever in how it works under the hood. So that's the quick overview of the design aspect of this. We will look next time on Monday about how the implementation works, and it's super cool.